This is your presenter Asloob Mudassar, and I am presenting slide number 72 of the course on laser physics. Question is, what are quantum well semiconductors? Discuss the physics of electronic transitions in QWS, that is in quantum well semiconductors. Also discuss density of states. The answer is, in quantum well semiconductors, a very thin layer of a smaller band gap material with band gap energy Eg1 is sandwiched between two layers of a larger band gap material having band gap energy difference Eg2, where Eg2 is greater than Eg1. Potential wells are established for electrons at the top of the valence band, represented by Vb, and for the holes at the bottom of the conduction band, represented by Cb. The width of the thin layer is made comparable to the size of the de Broglie wavelength of electron and holes. Due to this, electrons and holes confined in the respective quantum wells have energy levels with marked quantum size effects. So let me show you the description of this figure, that is a quantum well semiconductor. In figure 72.1, QWS quantum well semiconductor in A, that is this picture, and plots of energy as a function of Z coordinate in B, that is this one. So look at first of all picture number A. We have shown three dimensions of our quantum well semiconductor material: Lx along the x direction, Ly along the y direction, and Lz along the z direction. So the thin layer is coated between the larger band semiconductor materials. The smaller coating is within the two, as represented by the width Lz. Now look at the energy diagram of this one. You can see that there are two labels, Vb for the valence band and Cb for the conduction band. And these two levels for the valence band and the conduction band are due to the larger band gap material having band gap energy Eg2. So you can see that Eg2 is the band gap energy between the valence band and the conduction band, because these two bands are due to the larger band semiconductor material. So a thin layer of smaller band gap material Eg1 is sandwiched between two layers of the larger band gap material. So you can see that a thin layer of band gap material, semiconductor material, is sandwiched between two larger band gap semiconductor materials. And due to this, that is due to this sandwiching of the thin layer of smaller band gap material within the to be sandwiched between two layers of the larger band gap material, what happens? Quantum wells are formed. You can see that there is a quantum well connected with the conduction band and also with the valence band. The height of the quantum well in the valence band is represented by delta EV, and the depth of the quantum well in the conduction band is represented by delta EC. And you see that the difference of band gap energy between these two quantum wells is represented by Eg1, and obviously Eg2 is greater than Eg1. So you see that now the levels in the valence band, there are electron levels in this quantum well or in this step function, and there are levels corresponding to the hole vacancies in the conduction band, that is in the quantum well of this conduction band or in the step function of this conduction band. So there are energy states, that is the electron energy states exist in the valence band, and the whole states and the states corresponding to the missing electrons exist in the structure, in the quantum well structure associated with the conduction band. So you can see the energy gaps between these two. Potential wells are established for electrons at the top of the valence band. So you see that here VB, the VB level is actually the top level of the valence band due to larger semiconductor gap material. That is due to larger band gap material. So the upper level of that larger band gap material is represented by VB, and the conduction band is represented by CB. So you see that potential wells are established for electrons at the top of the valence band. So this VB level is actually the top of the valence band due to larger band gap material, and on top of this valence band the quantum well is formed above that one, and similarly the quantum well is formed below the conduction band as represented by the depth represented by delta EC, and the width of these two quantum wells is equal to LZ, as we have represented the width of these wells equal to LZ. Okay, potential wells are established for electrons at the top of the valence band and for holes at the bottom of the conduction band. The width of the thin layer is made comparable to the size of the de Broglie wavelength of electron and hole. Due to this, electrons and holes confined in the respective quantum wells have energy levels with marked quantum size effects. That is, the energy levels are well separated. I shall show you the energy levels later. Due to different lattice constants of the thin layer from the sandwiched material, strain develops within the thin quantum layers. Due to this strain, quantum properties of the quantum well semiconductor change considerably. One of such property is the change in the effective masses of the electrons and holes. This drastically changes the optical properties of the quantum well material from the bulk semiconductor material. So you see that two things are affected. One is the effective mass of the electrons and the holes due to this sandwiching of the thin layer among the two sandwiched between the two larger band gap materials. And the second is that the optical properties of the quantum material are changed in comparison with the bulk semiconductor material. The value of the electron transparency density, you see that we have discussed in previous slide, that is in slide number 71, about the transparency density in which the semiconductor materials becomes transparent. So the value of the electron transparency density for unstrained quantum well remains equal to the bulk semiconductor material, but decreases for the strained quantum well. So for the strained quantum well, we do not need to have a greater density of electrons to be injected as carriers. So a smaller amount will be enough in order to produce the same effects as produced by the bulk semiconductor materials or for the constrained quantum well semiconductor materials. Due to this, differential gain of the material increases considerably. Quantum well semiconductors offers enhanced mode gain. You see that different modes, different frequencies could be emitted by a semiconductor material when energized or when energy is supplied from outside. Different wavelengths, which we call different modes, are emitted. So these modes are called in general the modal gain. So the modal gains is enhanced in the quantum well semiconductors and decrease in laser threshold. You see that in order to produce, we need less amount of energy to produce the laser effect, as you can see that for the larger band gap material, the Eg2 is much larger in comparison with Eg1, which is due to smaller band gap material and due to the formation of the quantum wells in a quantum well semiconductor. So this smaller value of Eg1 means that there is a decrease in the laser threshold. Quantum well semiconductors are the most widely used semiconductor laser materials. So due to the properties, as we have mentioned earlier, that the most stable material for the lasing process in the field of semiconductors will be the quantum well semiconductors. Figure 72.1, that is this figure, explains the structure of the quantum well semiconductor. The well in the conduction band is represented by delta EC, that is the depth of the quantum well informed associated with the conduction band is represented by delta EC, and in the valence band by delta EV. Energy levels of electrons and holes exist in the corresponding quantum wells. That is, the electron levels will be formed, will exist in the quantum well associated with the valence band, and the holes or the vacancy of electrons, that is the energy levels corresponding to the holes or corresponding to the missing electrons, will exist in the quantum well associated with the conduction band. For simplification, we assume infinite depth of these wells, that is delta EC goes to infinity and delta EV goes to infinity. That is, these depths are infinitely large with band gap energy, that is delta Eg is equal to Eg2 minus Eg1. So you see that from this figure, that is in the part B of figure 72.1, you can see two energies we have shown, two band gap energies. One is Eg2 corresponding to the larger band gap material, and the other one is due to smaller band gap material, which is Eg1. And you see that if these quantum wells are not formed, then in order to excite an electron from the valence band to the conduction band, we need to provide an energy of the beam h nu greater than Eg2. So that band gap energy will be delta Eg will be equal to Eg2 when the quantum wells are not present. But when the quantum wells are present and we have the electrons at the top of the quantum well associated with the valence band, and we want to move that electron to the lowest state of the quantum well in the conduction band, then you see that the energy, that the minimum amount of energy that is required to fill this to overcome the band gap due to thin semiconductor band gap material will be equal to Eg1. So you need to supply the Eg1 energy if you want to move the electron from the top of the quantum well in the valence band to the lowest state in the quantum well of the conduction band. But for the other states, that is other states in the valence band to be, that is for the electrons lying in the other state of the valence band to be moved to the other states in the conduction band, the energy that is required to move that one will be equal to Eg, that is the delta Eg will be equal to Eg2 minus Eg1. So from this you can see that if if quantum wells are not formed, then Eg1 will be equal to 0 and delta Eg will be equal to delta Eg2. That is the band gap associated with the larger band gap semiconductor material. So you see that mixing the material with a thin layer provides us the opportunity to reduce the band gap energy for the excitation of electrons from the valence band to the vacancies in the conduction band. And remember that this is a 3D geometry, that is, it has a dimension of Lx, Ly and Lz. So we have the quantum wells are formed in the width Lz. And you know that we have said over here that the width, this width, that is lambda z, will be set equal to the de Broglie wavelength of the electrons or the holes. The infinite depth quantum wells in the conduction band represented by CB and in the valence band represented by VB along the energy levels are shown in figure 72.2. For example, this one. Let me read the caption of this figure first. First two energy levels in infinite quantum well in both the bands, that is in both the valence band and in the conduction band. We have shown two states in both these bands. So you see that these bands are actually what? These are actually the quantum wells we have shown over here. One quantum well associated with the conduction band, the other is associated with the valence band. So we have shown the two states in each of these bands, in each of these quantum wells. So these are the two quantum wells associated with the valence band, and you see that we have shown two states, that is n is equal to 1 and n is equal to 2 states in the valence band, and similarly the two states in the conduction band. In the conduction band, the first state represented by n is equal to 1 is separated by the energy from the base of this well, of this quantum well. The energy of that level is capital E and capital E 1c, and the energy of the level N2 correspond referenced with respect to the bottom of the quantum well in the conduction band is represented by E2c. And similarly for the valence band, you can see in the valence band, in the conduction band, the energy is measured upward because the energy is taken positively in the upward direction, whereas in the valence band the energy is taken downward is taken in the downward direction to be positive. So we have two states, N1 state and N2 state at energies E1V and E2V respectively from the top of the quantum well. So these are the two states we have shown in each. So you see that you can notice one difference, that the gap of energy, that is E1V, is not equal to E1C. And we have shown the level n is equal to 1 level at greater height in comparison to the n is equal to 1 level in the valence band. There could be many reasons, and one of the reasons could be the effective mass of the electrons and holes in these bands. Or generally I have drawn them differently so that any difference could also be accommodated in this picture. Otherwise these could also be identical with respect to each other. Okay, now you see that these are the two quantum wells, and I have shown energy states n is equal to 1 and n is equal to 2 in the conduction band, in the quantum well associated with the conduction band, and in the quantum well the same two level in the quantum well associated with the valence band. And the energies of these levels have also been shown. Now you see that I have also shown the wave functions. N is for the conduction band, for the conduction quantum well. We have for the n is equal to 1 state. We have shown we have also plotted the wave function for n is equal to 1 state as well as for n is equal to 2 state. A half wavelength is fitting in the width of the quantum well, and one wavelength is fitting for n is equal to 2 state in the quantum well. Similarly for the valence band, half wavelength is fitting in n is equal to 1 state of the valence band, and one full wavelength is fitting to the n is equal to 2 states of the valence band. So I think that the description is complete as far as this figure is concerned. Now the block wave functions, you see that we have plotted the wave functions at these two levels in the valence band and the corresponding and the conduction band, and you will notice that the wave functions for n is equal to 2 state in the conduction band is the same as n equal to 2 state of the valence band, and similarly the wave function which is equal to half of the wavelength is the same for n is equal to 1 state in the conduction band to the n is equal to 1 state of the valence band. The block wave functions would be the same for both bands and can be represented by. So we have psi c, that is the wave function for the conduction band, for the quantum well within the conduction band. Psi c as a function of r is equal to u1 as a function of r perpendicular multiplied by e to the power iota k perpendicular dot with r perpendicular, and then multiplied by the sine of n pi z over lambda z. And similarly, just replacing C with V, 2 stands for the valence band. The wave function, the block wave function for the valence band is given in equation number 72.2, which is psi V of R is equal to U as a function of R perpendicular multiplied by e to the power iota k perpendicular dot R perpendicular multiplied by the sine of n pi z over lambda z. So the two wave functions are identical because the quantum well has identical width equal to lambda z. And u of R perpendicular is actually the spatial part of the wave function. And e to the power iota k lambda k perpendicular dot with R perpendicular give you the phase information about the wave functions. Now let me explain these functions. So for example, n is equal to 1. If you put n is equal to 1 in equation number 72.1, in the sine function you have sine of pi z over lambda z. But you know that in order to find the wavelength, you need to multiply 2. You have now pi z over lambda z for n is equal to 1. Multiply 2 in the numerator and 2 in the denominator. The numerator becomes 2 pi into z and the denominator becomes 2 lambda z. So if you have 2 pi in the numerator and 2 lambda z in the denominator, it means that the wavelength lambda is equal to 2 times Lz. And then Lz is equal to lambda by 2 because this is the width Lz of each well. So in the Lz you have Lz is equal to, as obtained for n is equal to 1, we have Lz is equal to lambda by 2. So half wavelength will fit. Now if you put n is equal to 2 over here, you have 2 pi into z in the numerator and lambda z in the denominator. Since 2 pi over lambda, so lambda will be equal to z. So z will be equal to lambda in this case. So one wavelength will fit over here. So in order to find out the wavelength that is corresponding to lambda z, what you have to do is that you have to create 2 pi in the numerator. And then the rest of the quantities in the denominator will give you the wavelength, and from that one you can find what is the width of lambda z, how many wavelengths will fit into the width lambda z. So this is what I have explained, the wave function to be fitted in the n is equal to 1 level and in the n is equal to 2 level. And similarly for the other states, I have shown only the 2 states over here, but other states can also be possible. Where R perpendicular and K perpendicular are the components of R and K in the well plane, that is in the xy plane. And n is because you see that our geometry is 3-dimensional and we have R lambda, R perpendicular and K perpendicular defined, which are the components of R vector and K vector in the xy plane. N is a positive integer. In these two wave function definitions, n is a positive integer. So n is an integer value. Lz is the width of the well. Yc and that is psi c and psi v can be combined into a single notation, psi of cv. So since the wave functions, that is the block wave functions in the two cases are identical, that's for the conduction band and for the valence band. So rather than writing these two functions one by one, we are using a combined notation for the two wave functions, that is psi of c comma v. So this is the notations that we shall use, and this notation when we are only writing C, it will represent the wave function, block wave function for the conduction band, and when we are writing only V as a subscript, then it will represent equation number 72.2. The boundary conditions that the wave has to obey are, that is the wave function, block wave function is 0 for z is equal to 0, and also for z is equal to Lz. So on the left portion of these wells is located at z is equal to 0, and the right wall of the well is located at z is equal to capital Lz. So the one wall is at z is equal to 0, the other wall is at z is equal to capital LZ, because the width of each well is LZ. And you see that we are putting the condition that our wave function is vanishing for at the wall of the well. That is, the wave functions must vanish at the well interfaces. Similar periodic conditions hold for wave functions along the x and y directions, with kx is equal to L into pi over Lx, where L is an integer, and ky is equal to m into pi over Ly, where L and m are positive integers. So you see that if we consider the other dimensions and also the waves in the other dimensions, then those waves should also, that is the wave in the kx and ky direction, should also obey the boundary conditions. That is, the wave function must vanish at the well interfaces, at the walls of the semiconductor materials. But here you see that the things that is of interest to us is actually this width delta LZ. So this is important for us. So the waves in the other dimensions, that is along the Lx and Ly, are not important for us. We shall only consider the waves, and we have also listed down the wave functions, that is the block wave functions for the conduction band and for the valence band only along the dimensions of Lz. That is along the dimensions of the quantum well, because we have fitted the wave functions along this width, that is Lz width. Okay, so we shall be using only a single, you see that, psi of Cv. Okay, the boundary conditions that the wave function has to obey are: the wave function will vanish for z is equal to 0 and for z is equal to capital Lz. That is, the wave functions must vanish at the well interfaces. Similar periodic conditions hold for the wave functions along the x and y directions, with kx is equal to L into pi over Lx and ky is equal to m into pi over Ly, where L and m are positive integers. Within the periodic band approximation, eigenenergy values for both the bands are given by, that is, for the conduction band and for the valence band, we can write the energy, that is the eigenenergy of the system. So we have E, Cv. For example, we are representing the wave function as a psi with subscripts C and V. Similarly, we are writing down the eigenenergy with a subscript C and V. So E with a subscript CV is equal to h bar square k perpendicular square over 2 mCv plus h bar square kz square over 2 mCv. So you see that this is actually principal, this energy is actually principal h bar square over 2 mc, and then multiplied within parentheses we have kx square plus ky square plus kz square. But we have separated kx square and ky square because as seen in equation number 4, we are representing kx square plus ky square is equal to k perpendicular square. So we have absorbed kx square and ky square in the k perpendicular square in the first term of the energy in equation number 3, and the second terms only represent the dependence on the wave number kz, where kz is equal to n square into, because k is similar, since we have defined kx is equal to L into pi over Lx and ky is equal to m into pi over Ly. Similarly, we define kz is equal to n into pi over Lz, and the square will be equal to kz square is equal to n square pi square over Lz square. So you see that we have not solved the Schrödinger equations, and we have not solved the system quantum mechanically, but we have just obtained the result, and we are just discussing the result of that. So this is the eigenenergy states. Okay, where mCv is the electron mass in the conduction band or the whole mass in the valence band. The energy levels are represented by solid lines, and the wave functions are dotted lines in figure number 72.2. For example, in this figure, you can see that the horizontal lines corresponding to n is equal to 1 and n is equal to 2 in the valence band, and similarly the solid horizontal lines corresponding to n is equal to 1 and n is equal to 2 represent the energy levels or the energy states or the states available in the conduction band and the valence band for the first two states in the conduction band and the valence band, and the wave functions has been shown by the dotted lines. If you look closely and magnify this figure, you will see that the wave function has been plotted in dotted. Let us introduce the energy of the first quantum state corresponding to n is equal to 1, valid for conduction and for the valence bands as well. So let's write the energy of the quantum well state for n is equal to 1. So putting n is equal to 1 over here, we have this E1, because we are using 1 in order to stand that we are using n is equal to 1 over here. So we have E1 with the CV other subscripts is equal to h bar square pi square over 2 mCV multiplied by Lz square. Because in this expression we have substituted the value of kz, which is equal to n square pi square over Lz square, and we have replaced n by n is equal to 1 value, and the rest of the quantities are written over here. But you see that in order to write this expression, we have used k perpendicular equal to 0. For example, this will be clear over here. So you see that here we are plotting, for example, k perpendicular, and if we here in the center, that is in this region, k perpendicular is equal to 0. So if you are using a k perpendicular to equal to 0, then you are getting the energy E1 CV is equal to h bar square pi square over 2 mCV into Lz square. So we can write this equation, that's the equation number 3, in this form, that is ENCV, because now we have introduced n. So we have n, C, V. So E has 3 subscripts now. ENCV is equal to h bar square k perpendicular square over 2 mCV plus n square into E1 CV, because we are now using this E1 CV. Because this will for a next state we have to put n is equal to 2 in equation number 7 to get the energy corresponding to the state 2 in the conduction, either in the conduction band or in the valence band. So you see that here from these expressions it is clear that the energy states exist at the same energy level, because the right hand sides are the same for the conduction band and for the valence band. So in principle, these two energy levels, that is the energy states in the valence band and the energy states in the conduction band, should occur at the same heights and the same depth in the conduction band and the valence band respectively. For finite depth quantum well, electrons are not totally reflected at well interfaces. So you see that the previous assumption that we have made, that our wave function vanishes at z is equal to 0 and z is equal to Lz. This is now, we are not restricting to that one, because we have for a finite depth quantum well, electrons are not totally reflected at well interfaces, and the above stated boundary conditions will not be applicable. Consider the case when electrons have zero transverse momentum, k perpendicular equal to 0. So k perpendicular equal to 0 means that we are considering the electrons that have zero transverse momentum. That is, the electron is only moving towards the z-axis and is not moving, is not deflected towards either of the kx or ky plane. The energy levels in both the bands are indicated by equation number 72.2, which we have discussed earlier. Now consider the case when the electrons have k perpendicular greater than 0 and ECV versus K perpendicular plots are shown in figure 72.3 for n is equal to 1 and for n is equal to 2. So let me show you that figure. For example, this figure. This is figure 72.3. Here we have plots of CV. On the left hand side we have plots of CV, that is the plot of C along the positive direction, the plot of EV along the downward direction, because the energy of the valence band is measured positive downward and the energy of the conduction band is measured positive upward. So we have ECV versus K perpendicular for n is equal to 1 and n is equal to 2 sub-levels in both the bands, that is in the valence band and for the conduction band. So you see that here you can see that we have the valence band, and for the valence band we have a separate K lambda, K perpendicular horizontal axis separately for the valence band, and we have K perpendicular horizontal axis separately for the conduction band. Okay, and the plot of transformed energy E prime versus K perpendicular in part B, which we shall discuss after discussing the part A. So you see that here you can see that there are two parabolas in the valence band corresponding to n is equal to 1 and corresponding to n is equal to 2. And this parabola is due to your expression of energy, because we have K perpendicular square. Due to this K perpendicular square, the equation of E versus the plot of E versus K perpendicular will be a parabola, because this resembles the equation of the parabola. So for n is equal to 1, you have the parabola over here, and for n is equal to 2, you have the second parabola further downward in the valence band. These parabolas are existing at energies EV1 and EV2. That is the vertices of these parabolas exist with respect to the K axis downward at energies EV1 and at energies EV2. And similarly for the conduction band, there are two states, n is equal to 1 state and n is equal to 2 states. For example, over here we have two states represented by a line over here, n is equal to 1 and the line corresponding to n is equal to 2. But in reality, when we plot these energies, that is the energies that we have obtained, for example in equation number 72.3 or for example in equation number 72.7, if we plot these energies versus the K number, we get a parabolas. So we have two parabolas in the conduction band corresponding in the conduction well, quantum well, corresponding to n is equal to 1 state and corresponding to n is equal to 2 state along the conduction along the energy EC, which is taken positive upward. And these the vertices of these parabolas are at the energy location, at the energy height EC1 from the horizontal axis K perpendicular, and the other parabola is at an energy of EC2 from the K perpendicular axis. The solid dots in the valence band along the parabolas represents the possible states which are occupied. So the solid circles represents the electron states occupied in the valence band, and the hollow states or the holes vacancies, you can say these are the empty states, or you can say these are the whole states, that is the missing electron states, or these are the states that are available for the electrons from the, if moved from the valence band, then these are the possible states for the electrons to occupy along the parabolas represented by the hollow circles. And you know that these parabolic states actually exist within these quantum wells. For example, the quantum well along the associated with the valence band, and the quantum well associated with the conduction band. So we have these parabolas instead of these horizontal energy axis corresponding to n is equal to 1 and n is equal to 2 in both bands. Actually, these are the parabolas corresponding to n is equal to 1 and n is equal to 2, which we have shown over here. So these are formed in the quantum wells. So the electron states, which are the fully occupied states in the valence band exist in the valence band, and the empty states exist in the conduction band. So we can move the electron from the valence band to the conduction band by providing appropriate energy by okay. And you see that here I have marked that the two states are separated by a distance pi over lambda perpendicular along the k lambda direction. K perpendicular direction. You know that the k perpendicular is actually the square root of kx square plus ky square. That is, when we plot k perpendicular, it means that we are plotting the wave number in the xy plane, where the distance can be represented by capital L perpendicular. So these two states along the xy plane is separated by pi over lambda by pi over L perpendicular. Now you see that here we are, since we have two horizontal axes, k perpendicular, a separate axis for the conduction band, and k perpendicular horizontal axis separately for the valence band. The reason is that we are measuring the energy of the conduction band with respect to the upper horizontal axis represented by k perpendicular, and we are measuring the energy of the states in the valence band with respect to the lower k perpendicular axis. But you know that if we set the same axis, for example, if we set over origin for the measurement of energy at the lower k perpendicular axis, then of course we need to remeasure the energies with respect to this axis. And this is shown, you know, that on the diagram. In the diagram on the right hand side, we have the two parabolas again, corresponding to n is equal to 1 and n is equal to 2 in the valence band, and similarly two parabolas facing upward in the n is equal to 1 and n is equal to 2 in the conduction bands. And now we have energies E prime. So E prime is the energy which is positive along the positive direction. So you see that we have shown here two states represented by E prime 1 0 in the valence band and E prime 2 0 in the conduction band. And now we can move the electron from the state E prime 1 0 to the state E prime 2 0 by providing an energy E naught, which is equal to h nu naught. So if you provide this much energy, you can move an electron from the state shown in the valence band to the state shown in the conduction band. Figure 72.4. That is this figure, but I am coming to this figure soon. So let me read some description. Figure 72.4 represents allowed states in the kx, ky and kz space for n is equal to 1, denoted by the dots. So you see that in this figure, these dots represent the allowed states available in the n is equal to 1 state in both the valence band and the conduction band. You see that I have we have three axes in the k domain: kx, ky and kz, and this plane is existing at a distance pi over lambda z along the kz axis. And this kz axis is now a plane. At a plane, we have n is equal to 1, we have a plane there, and this plane is actually the plane determined by the kx and ky coordinates. And you know that the horizontal lines are separated by pi over pi divided by lx. That is the horizontal lines, and if you see that these vertical lines are separated by pi over ly. So along the ky direction, the separation between these states is pi over ly, and the separation between the states along the kx direction is pi over lx. So these are the states that we have shown. And you see that the dimension of this level is determined by the dimension of kx and ky, that is the dimensions of the main chip. So the caption is available states in the n is equal to 1 sub-level in the kx, ky and kz space. So the figure 72.4, which we have just discussed, represents the allowed states in the kx, ky, kz space for n is equal to 1, denoted by the dots. They are separated by pi over lx along the kx direction, pi over ly along the ky directions. Lz is usually 3 to 4 orders of magnitude smaller than Lx and Ly, because Lx and Ly have got larger dimensions in comparison with Lz, 3 to 4 times in magnitude. The two successive states along the kz directions are separated by delta kz is equal to pi over lambda z. The meaning is that the next level, the next plane will correspond to n is equal to 2, and that will be separated by another distance equal to pi over lambda z. So the difference between the two states along the kz direction will be equal to delta kz is equal to pi over lambda lz. The allowed states lie in the planes orthogonal to the kz axis. You see that these states lie orthogonal to the kz axis. Similarly, for the states in the n is equal to 2 level also lie orthogonal to the kz axis, and the planes are well separated. The density of states in these planes can be calculated. K perpendicular lies on the kx ky plane. Let capital N as a function of k perpendicular be the number of states in each plane lying between 0 and k perpendicular. Then k perpendicular, then k as a function, then n as a function of k perpendicular is defined as n as a function of k perpendicular is equal to 2 times 1 over 4 multiplied by the area of the circle of radius k perpendicular divided by the area of the unit cell. You know that here we are considering the area of the circle of radius k perpendicular. But at the same time we are saying that we want to calculate the number of states lying between 0 to k perpendicular. So it means that we are considering the states only along the positive quadrant. That is the quadrant determined by positive value of kx and positive value of ky. For that one we are dividing this area of the circle by 1 over 4. And this factor 2 comes from the two possible states for each electron due to the spin, because the spin could be up or the spin could be down for the electrons. So that's why in order to account the number of states we are multiplying by the factor 2 in the numerator, and in the denominator we are dividing it by the unit area, and the unit area is given by delta kx multiplied by delta ky, and the area of the circle in the numerator is given by pi into k perpendicular square. So computing this one and representing, introducing the area of the plane, we are writing it on the right hand side as k perpendicular square multiplied by a perpendicular divided by 2 pi, where a perpendicular is equal to lx into ly is the transverse area of the quantum well, because lx and ly are the real dimensions of the chip. So these are the transverse area of the quantum well. Transverse in the sense that perpendicular to the z direction. Now let rho k denotes the number of states per unit k perpendicular unit area. Then we can calculate rho k from equation from n of k perpendicular using the formula, that is rho of k is equal to dividing it with lambda area, because we are calculating at per unit area. So we have 1 over a perpendicular, and we are also calculating the number of states per unit k perpendicular. We cannot divide it, k perpendicular cannot be divided, but we need to take the derivative of n of k perpendicular and the derivative with respect to k with respect to d k perpendicular, and the derivative of the above equation with respect to dk will, and introducing the value of the variable of the area, we get the value that rho of k is equal to k perpendicular over pi as given in equation number 9. This equation is valid for both valence and conduction bands. The density of states in energy coordinates is obtained from this expression, that is the rho Cv multiplied by d multiplied dE Cv is equal to rho k multiplied by dk perpendicular. And from here we can find rho Cv is equal to rho k, and on the right hand side with also dk perpendicular, the derivative of dk perpendicular with respect to dE Cv. So using the value of rho k from this equation, we are writing the expression in equation number 10 as rho Cv is equal to k perpendicular over pi, and then the derivative of dk perpendicular over dE Cv. So d, that is the derivative dk perpendicular over dc over dEc can be obtained from equation number 72.6 and 72.7 for the case of n is equal to 1, and we obtained the following equation. So let's look at equation number 6 and 7. These are the two equations. So we need to calculate, we need to solve this equation for k perpendicular, and then we need to take the derivative of k perpendicular with respect to the energy to get the derivative that is required in our equation, that is in equation number 10. So substituting that value in equation number 10, we obtained the equation as given in equation number 11, that is k perpendicular square is equal to 2 times mCv over h bar square, and we have multiplied within the parentheses the difference of energy, that is ECV minus E1CV. So this is the value of k perpendicular square that we have obtained from the previous equation, and then taking the derivative of this k perpendicular with respect to the energy and substituting in equation number 10, we obtain the value of rho Cv is equal to mCv divided by pi into h bar square as shown in equation number 12. You see that rho Cv is thus independent of k perpendicular and thus independent of the transverse part of the energy, which is represented by h bar square k perpendicular square over 2 mCv. So over this rho, that is the density of states, is independent of k perpendicular. The density of states for energy greater than the energy of the state 2 either in the conduction band or in the valence band is then the sum of densities of both n is equal to 1 and n is equal to 2 sub bands. That is, if we want to calculate the density of states for an energy beyond the second level of the energy, then we need to incorporate the energy then we need to incorporate the density of states corresponding to n is equal to 1 and n is equal to 2 sub levels or sub bands. The analysis for conduction band is valid with the subscript C, and for valence band this is valid for the subscript if is valid for subscript V in the above equations. You see that in the above equations we have been using two subscripts together, that is the C standing for conduction band and V standing for the valence band. So if you want to write the calculations only for the conduction band, you can omit the second variable that is V. And if you want to write the calculations for the valence band only, you can retain V and you can omit C from these calculations. So here CV means that the calculations are valid both for conduction band and for the valence band. And you see that we have addressed the problem, we have calculated the requirements that were asked in the questions. We have met those requirements in this lecture. So this is the end of slide number 72.